Hey everybody, welcome back to another classroom. So yesterday we talked about AM, FM radio broadcast signals. Today what I want to talk about is called the Doppler Effect. And so I think you may have heard of the Doppler Effect, but it has to do with frequency. And I think we've all heard the ambulance or the fire truck going by. As it approaches us, it sounds a little bit more high-pitched. And as it goes past us, it gets loud and then it starts to fade. But as it fades, the pitch also starts to decrease. And that's called the Doppler Effect. And that's called the Doppler Effect. And the reason for that is this. So I have the example here. Here you are. There's another person standing over there. But here's the ambulance. And as it's going really fast, its siren is making noises, and the sound waves are traveling at the speed of sound. But because the vehicle is also traveling, it is starting to squish or compress the sound waves in front of it. And you know from frequency that the more sound waves per second equates to a higher frequency, a higher pitch. So all the sound waves in front of the ambulance as it's going in this direction are getting compressed. And so people standing in front of the ambulance, or as the ambulance is approaching them, they start hearing a higher pitched siren. As the ambulance passes you, because it's going that way, the waves that are behind it start to get stretched out, and that means less waves or cycles per second, lower frequency, so you hear a lower sound. Kind of like, I'm not even going to do it. Here you can see a source of sound moving to the right, and the sound waves in front of it are being compressed, while the waves behind it are being elongated or stretched out. Okay, so anyways, that's all you have to know for today. It's the Doppler effect. And so scientists use this with radar. We use it to see if objects in the sky and the universe are moving away from us or coming toward us. If they're moving away from us, they call it a redshift, because in the spectrum, Roy G. Biv, if it's moving away from you, the frequency shifts lower. And so in color, if you were looking at a star, it would shift toward the red range. If the star is moving towards us, or the object's moving towards us, and you're looking at it and it's giving off light, instead of shifting to the red, it would shift toward the blue, and that would tell us that it's actually accelerating, coming at us. So it translates visually to light waves. You can see that, the Doppler effect. It's called the redshift. And with sound waves, it's just called the Doppler effect. In this example of the redshift, you can see as the light source is moving towards you, the light shifts into the blue range. And as it's moving away from you, as they get stretched out, they shift to the red.
What time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. You know, most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
I'm Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.